Alright, welcome back. MECH2320. Alright, and we're getting into chapter 4 here. We're going to talk about resistors and reactor starting for AC motors. Okay, so in general, why do we do this? Okay, well, for the most part, it's because your power systems can't necessarily handle the inrush of current. Because when you fire these up, alright, there's a huge inrush of current into these systems, and sometimes that trips the power breakers and things like that. Just the way it was designed, and it's for protecting equipment and things like that as well. So when we do this, all right, there's a couple different methods we're going to employ. It's just to limit the inrush current. That's all we're doing, and there's a couple methods that we're going to talk about when we do it. So that inrush current, so we don't tear down the main power system or things like that. But we reduce the starting current, and like I said, it's in conditions where it's not possible to start a motor across the line because of the inrush current. So two different methods we're going to talk about are resistor starting and reactor starting. So resistor starting, okay, what we're doing, we've talked about this briefly in a prior lecture. We're going to put resistors in series with the motor during the starting period. That's the important part, is during the starting period. These resistors don't stay in the circuit the entire time the motor's running. It's only in the starting period when there's that inrush of current. Once the motor operates at a specified speed, all right, those resistors are tapped out of the line. Okay, so you can see here's a schematic of what that looks like. We're looking at the power portion of the schematic at the upper part of the diagram here that's highlighted in blue. We have 3 resistors, each in parallel with the motor, and then what we have, we're going to call it in shunt, but it's in parallel. Okay, notice that we have a normally open resistor contact for each one of those, because when we get up to a specific time, okay, so this is using a timer relay to close the resistor contact. So we're going to go through a couple of methods of how we drop the resistors out of the circuit. But in this case, using the normally open contactors and looking at the schematic down below, okay, we have a off delay timer relay. That's at the very bottom of the schematic there, okay? So we're going to use an off delay. So what we do is when the motor starts, okay, the current's going to come in through the lines, through the resistor, and that resistor is going to make it so, we don't get an inrush of like 200 amps when we only need 100 amps or something like that, okay? What's going to happen, we hit the start button, okay, the motor turns on, the seal-in logic turns on, the motor contactor down here in the second rung closes. That turns on the delay. I'm sorry, did I say off delay? This is an on delay timer. On delay, I misspoke there. Let me correct that. What happens here is that motor contactor closes, okay, and then we have the on delay. So we know that after a certain amount of time, the current is no longer a high current, it's leveled out. So we can say, okay, after 5 seconds, okay, the motor has been on, then we'll turn on the contactor for the resistors so they bypass the resistors. So hopefully that makes sense there. So sorry about it. This is a on delay timer. I misspoke there. So when the timer closes, okay, it's going to count to say 5 seconds. 1, 2, 3, 4, 5. When 5 seconds hits, all right, or after the coil's energized for 5 seconds, the timer's going to close, okay, and then the resistor contacts will close. And remember, all the current's going to go through those contacts now instead of the resistor, because current takes the shortest or the least path of resistance. So there will be very little current going through those resistors, if any at all, and it's like we're shorting out the resistors on purpose. Okay, and then it'll be up and running. Essentially, that's how we, eliminate inrush current. Okay, another method is if we use a Hall effect sensor, and we put a Hall effect sensor to detect the speed of the shaft, kind of like when you guys use the tachometer in the motor control class. All right, or not the motor control class, that's what we're in the mechanical class. Sorry, it's one of those days, I guess. In the mechanical class where you guys, check the motor speed and things like that, we can put a Hall effect sensor on there to determine what the motor speed is. So instead of using a timer and assuming, all right, after 5 seconds, we're going to bypass the resistors, we can use a Hall effect sensor and detect when the motor gets up to a certain amount of speed. Alright, so when the motor gets to a certain speed, alright, after it's turned on, that sensor is going to close, and then the resistor contacts will close, bypassing the resistors. So just remember, motors, in electrical we call it, it's a parallel contact. In motors, we don't like the word parallel, we call it shunt, even though we keep series the same, okay? So this is, when we're talking about shunting the resistors out, we're talking about paralleling them out. We're really talking about shorting them after the motor gets to a specific speed. So we're shorting around the resistor. Essentially, that's what we're doing to get the motor running. All right, and remember, this is all just to prevent the inrush of the current, okay? We can also place a current sensing device on there as well. All right, just like, when we can go out and do a clamp meter, we can put a device that's on there just like that, okay? And it will detect the current. So what it's going to do is, as long as the current's at this particular amperage, all right, we're going to, bypass or go through the resistors to the motor. But then when the current reaches the specified current setting, okay, then we bypass or we shunt out the resistors. So the current sensors, working the exact same way that the Hall sensor would, as far as reading that, only instead of reading speed, we're reading current in the line. So there's another method of how we're doing it. So that's the resistive methods that we're talking about there. All right, we've got the resistor in series, okay, and we've used multiple methods to detect when the current's right. One's a timing method, okay. The other one that we used was speed or RPMs of the motor, and then this last one is a current sensing device on each line that we know that, all right, the current's at the operating current, we're good to go. Let's short through the resistors here and let the motor run. So all good for startup, preventing inrush of current here. All right, so when we get into reactor starting, it's going to be the same concept, okay, same concept, only we're going to use a reactor instead of a resistor, okay. When we use a reactor in this case is going to be our inductors, okay, so we're going to use an inductor. All right, so remember, an inductor is just a coil of wire storing a magnetic field, so we can use the inductive resistance instead. Okay, so when we use remember when we use inductors and capacitors and things like that, everything works at an exponential rate. Now I know in the electrical class we didn't talk about inductors, and we haven't talked about them, in general, but for the most part, an inductor sort of acts the same way as a capacitor does, only capacitor is storing charge and inductor is storing a magnetic field. So we can use that against it. And the way inductors and capacitors work, right, we have like a charging discharging kind of phase, right, and it's about exponential growth and exponential decay. So we can use that to reduce the inrush current as well. So notice now we have the reactor, okay, it's really just an inductor, and remember the two bars on the inductor mean that it's an iron core on that piece, so it's wire wrapped around an iron core. Or so essentially we just got 3 coils on the starter right there, okay. So what's going to really happen is that those coils, since we still have the resistor contact in parallel or in shunt, right, with the reactor, we're forcing the current to go through the actor, and based on the coils, okay, remember those are going to kind of act like a transformer or things like that, so we can step down how the current's going through there. That's kind of what we're doing in that aspect. Okay, so, and then we know, since we're limiting what's going on there, we're kind of capturing the field. We're using it as a filter, okay, kind of like how you use an RLC filter in your stereo to turn to a specific frequency for a radio station, things like that. Okay, so we're using it as a filter so that it holds the current from going into the motor and blowing it up, sort of thing. Not literally like a bomb or anything, but ruining it, making it smoke, and that sort of thing. So with these, all right, notice if we look at the schematic, we still have an on delay timer there. So we're going to control how much current's going to the motor. We're or stopping, like it's kind of like just putting on a small little floodgate stop there for a second. Okay, and then once the motor turns on, all right, then the timer coil turns on and starts counting, counts 1, 2, 3, 4, 5, and then the on delay timer closes, which closes the resistive contacts, and then we short around the reactor. So very, very similar of how we did the resistor one. Okay, because here's what's really happening here. Remember that in current here, right? If we have the resistance current, remember, since the resistors are in series, all right, this is comparing the two methods here. When the resistors are in series, right, there's one current that goes through there, so our current will be constant. Okay, when we have current that's inductive, okay, it exponentially grows, so it won't even start out at the constant that the resistive current grows. Okay, inductive current, just like capacitive, like charge, grows exponentially. So remember, capacitors, like I said, we always talk about charge and those things, and charge over time. Well, we're talking about current here with the inductor, so it also grows exponentially, and then we get to that specific point. Okay, so it's just a way of how we, when we're growing this way, we're slowing it down. Actually, you know, even though exponential growth is fast, right? We understand that. It's still starting out slower than if we were using resistive current, because, right, resistive current is immediate, it's right at that value. Inductive current, right, we're still starting at 0 and ramping up. So that ramp up time, remember tau that we talk about, and the relationship between time, the inductor, and the property of the materials there actually affects what the growth rate is on that circuit. Okay, so we could do step starting. Okay, so there's multiple ways of doing step starting. So we can actually tap the resistor or the reactor. So what does that do for us? That's changing different values of resistance or inductive reactance. Okay, and I know I keep throwing inductors at you, and we've talked about capacitors, but they're very similar. So I just want to relate one more term for you. And you know, where does this come from? Reactance. Remember when we did capacitors in the electrical class, okay? And you had to find the reactance, because capacitors had two properties, right? They had capacitance and they have reactance, and you had to find the reactance 1 over 2 pi Fc, all right? And it was 2 pi times frequency times capacitance, okay? Remember, every capacitor had a specified resistance with it. Inductors do the same thing, okay? They have an inductance, okay, it's magnetic field, and they also have a reactance piece to them, a resistance piece to them. So that's where that's coming from. And remember, we call it a reactant because it's dealing with a capacitor. It's still a resistance, okay, but we can control that resistance by, you know, allowing the current to grow exponentially. So I know we didn't hit a ton on inductors, but there's kind of a brief overview, so hopefully that kind of fills that in. And then when we tap it, we're tapping it just like a transformer. All right, so for different starts and things like that. So we can still center tap that inductor, okay, to do, you know, what we want to get different currents. Okay, so that's how we could do it. So you might have like a universal kind of reactor piece, and you can adjust the reactance. All right, think of like an adjustable resistor. You can adjust the reactance here based on how you're tapping that coil, all right, for the amount of inrush current that you want to or need to make sure that the motor will start and run properly. So, all right, guys, that's the end of this lecture. Hopefully we learned a little thing about limiting inrush current using resistors and reactants, and that reactant happens to be an inductor in this case. Alright, but as usual, email me if you have any questions. Else, guys, have a great day, and I will see you in class.